In this video, we're going to talk about solving quadratic inequalities. A quadratic inequality, for example, is something like this: x squared plus 5x minus 6. There's my quadratic, and to make it an inequality, I use an inequality sign and put some number on the other side. So this is asking, for what values of x would this be true? And we'd be asked to solve that. Before we get to quadratic inequalities, let's review the properties of inequalities by looking at some linear inequalities. Let's begin with a statement we know is true: 3 is less than 5. Well, what can I do with this legally and what can I not? Let's try adding 2 to both sides. If I add 2 to both sides, I get 5 is less than 7, and we know that that's true. What if I subtract 3 from both sides? Then I would get 0 is less than 2. Also true. So we can see that adding or subtracting the same number to both sides maintains the truth of the inequality. So this is working like a regular equation would. What about if we multiply both sides by 2? If I multiply both sides by 2, I would get 6 is less than 10. Again, that's true. If I divide both sides by 2, I'd get 1.5 is less than 2.5. And again, that's true. That was dividing by 2. What if I multiply both sides by -1, however? Then I would get -3 on the left side is less than -5. And if you think about it on a number line, -5 is to the left of -3. So this is a false statement. So that was incorrect. So there's something illegal about this multiplying by -1 and just leaving it as we did here. Similarly, if I divide by -1, then I would get the same thing. -3 is less than -5. Also wrong. Notice though, if I flip the signs here, so if I multiplied by -1, I got -3 and -5, but then flip that sign in the middle so that it pointed like that, now it would say -3 is larger than -5, and that's now a true statement. So the rule we need to remember when dealing with inequalities is when you multiply or divide by a negative number, you have to reverse or flip the sign around in order to maintain the truth of the statement. So if we look back here, we can add or subtract any number and multiply and divide by positive numbers without doing anything to the sign. But as soon as we multiply or divide by a negative number, we have to reverse the sign, flip it around, in order to maintain the truth value of the statement. So now let's look at some examples. We're going to solve these linear inequalities and then graph the solution on a number line. We're given 3x minus 4 is greater than or equal to 5 and asked to solve for x. So first we're going to get rid of this -4 by adding 4 to the left side. If we add 4 to the left side, we add 4 to the right. So on the left side, we just end up with 3x, and on the right side, 5 plus 4 is 9. Now we divide both sides by 3 to get rid of this 3. So on the left side, I have x, and because I'm dividing by a positive number, I don't have to flip the sign. I still write my greater than or equal to, and 9 divided by 3 is 3. So when x is greater than or equal to 3, this statement will also be true. 3x minus 4 will be greater than or equal to 5 as long as x is greater than 3. And you can check that by plugging any number that's 3 or greater in here for x, and solving on the left side, you'll get a number that's greater than or equal to 5. Now, to plot that on a number line, just very simply, here's a number line with my 3, my number of interest on it, and to show anything greater than or equal to 3, I would color in the 3 to show that 3 is included, and then put an arrow like that to the right. Some people will color right in on the number line like that. Either way is fine. This is showing any number 3 or greater. Let's look at a slightly more complicated one that has 2 inequality signs. The rules still apply. If I want to do anything to any one of these parts of the inequality, I have to do it to all the others. So it's kind of like having multiple equal signs. Here we have multiple inequalities. So I want to isolate the x. The first thing I'm going to do is get rid of that 1. To get rid of the subtraction of 1, I add 1. So I'm going to add 1 to the middle. That gives me 2x. If I add 1 to the middle, I have to add 1 to the left and the right to maintain the inequality. So if I've added 1 here, I have to add 1 to the -3. That gives me -2. And if I added 1 in the middle, I have to add 1 here. So 5 plus 1 is 6. Carrying on, I need to divide out this 2. So 2x divided by 2 is x. Dividing by a positive number, I don't have to reverse the inequality signs, but I have to divide the left side by 2. So -2 divided by 2 is -1. And the right side, so 6 divided by 2 is 3. This tells me that when x is strictly between -1 and 3, meaning it's greater than -1 but not equal to -1, and less than 3 but not equal to 3, then this statement will be true. Graphing this on a number line, again, I'm going to draw my values of interest here, -1 and 3, and because -1 is not part of the solution, there's no equals here as there was on this one, I'm going to draw an open circle on the -1 to show that -1 is not included in the answer, and similarly an open circle on +3. Some people will color in the line in between the two of them boldly, or you can draw this kind of thing. It's kind of like an arrow that goes all the way from one to the other to show that that's the solution. So that's solving linear inequalities, graphing the solutions on a number line. Now before we get to the quadratic inequalities, let's do one more thing and review how solving for x is the same as finding points of intersection. If you were given this simple linear equation, 3x minus 1 is equal to 5, and asked to solve, you'd add 1 to both sides, getting 3x is equal to 6, and divide both sides by 3, getting your solution, which is x is equal to 2. You could also solve it graphically, though, by graphing the left side of this equation, so let's call that y1 is equal to 3x minus 1, and graphing the right side of the equation, so let's call that y2, and that's equal to 5, and finding the points of intersection. So if this is my Cartesian plane, and I graphed y is equal to 5, that would be a horizontal line 5 units up from the x-axis, and we'll call that y2. And if I graphed y1 is equal to 3x minus 1, it's got a slope of 3 and a y-intercept of -1. So it might look something like that. And graphing those, you would find that their point of intersection has an x value of 2. If we trace that down to the x-axis, we'd see it has an x value of 2. So finding the solution to this equation algebraically gives us the same answer as finding the solution graphically. Finding graphically, what we do is we graph the left side, y is equal to 3x minus 1, and the right side, y is equal to 5, and find the point of intersection. Now if we move on to solving this inequality, which is related to this one, it's again the same two functions, y is equal to 3x minus 1 and y is equal to 5, but now it is asking when is this function greater than this? When is the y value for this greater than the y value for this? And on the graph, what that means is, when is this function above, physically above, higher on the page than this function? If we look at the curves, or the lines rather, here, everywhere to the right of 2, we see that the graphs have crossed over, and this line is above the horizontal one. So everywhere to the right of 2, in other words, when x is greater than 2, this line is above that one. And so that would be the solution we would get graphically to this inequality. We can also see that if we solve this one algebraically, we add 1 to both sides, we get 3x is greater than 6, and then we divide both sides by 3, we get x is greater than 2. Same thing. So solving graphically gives us the same answer as solving algebraically, and in some ways is a little bit easier when things get more complicated, as we'll see in a moment, because we can picture one function being physically above, higher on the page than the other. So let's now look at quadratic inequalities. If we're asked to solve this inequality, x squared plus 5x minus 6 is greater than 0 for x, we can think of that graphically as we just saw, and in that case it's asking for what values is the parabola represented by the left-hand side of the equation, so y is equal to x squared plus 5x minus 6, we'll call this y1, above, higher on the page than the line y2 is equal to 0. And we know that this is just the x-axis. So now we're asking, when is this parabola above the x-axis? And we're going to solve that by sketching. So the first step would be, if the question were a little harder, we'd have to move everything to one side of the inequality first. So for example, the question could have started off as x squared plus 5x is greater than 6, and then we want to move this 6 to the left-hand side by subtracting 6 from both sides. Here it's already done for us. Then we would factor the quadratic to find the x-intercepts. So in this case, we're looking for two numbers that multiply to -6 and add to 5. Those numbers are positive 6 and 5, so this factors to x plus 6 times x minus 1, and then we've got our greater than 0. So as we just saw then, now we're asking, when is this parabola above the x-axis? So we can sketch out the parabola. We know that it has an x-intercept of positive 1 and an x-intercept of -6. And it's opening upwards because the leading coefficient is positive, so it's going to look something like that. We don't have to be more precise because all we're trying to figure out is when is this graph above the x-axis. And now we can see that here the parabola is above the x-axis and here the parabola is above the x-axis. Expressing both of those parts of the number line as an inequality, we see it's when x is less than -6. So everywhere to the left of -6, the parabola is above the x-axis, and everywhere to the right of +1, so when x is greater than 1, the parabola is above the x-axis. So that means that this parabola is above the x-axis. We can check if we would like by plugging in numbers. So plug in a number greater than 1, let's say 5, you would get 11 over here, times 4, 11 times 4 is 44, which is greater than 0. Plug in a number left of -6, let's say -7, you plug in -7 here, you're going to get -1. You plug in -7 here, you get -7 minus 1 is -8, so -1 times -8 is +8, which is greater than 0. So that's how you solve inequalities by sketching. If the question were slightly different and this was a less than sign, then we'd end up getting the same sketch because parabola would factor in the same way, x plus 6 times x minus 1, but now we'd have less than 0, so the sketch looks the same until we draw the parabola. But now we're asking when is the parabola below the x-axis, so that's in here, and that would be -6 is less than x is less than 1. We're asking for numbers between -6 and +1, and that's how we would write it. Now, if the question had been slightly different and this had been a greater than or equal to sign, and so this and this had also been greater than or equal to signs, then the same would be true for our answer. All of these less than and greater than signs would also be less than or equal to and greater than or equal to signs. Because if we look back here, when x is equal to -6 or x is equal to +1, then we actually get an answer equal to 0. So we'd have to include these as well. So that's how the question would change if it was this kind of inequality. And that's an introduction to solving quadratic inequalities by sketching.